Welcome to another TIRIAScast. I'm Jim McGregor. I'm here at Supercomputing 2025 with Sam Stanwyck. And ironically, this is usually an HPC conference, but quantum actually kind of seems to be stealing the show. I've had more conversations on quantum than I have any other topic here so far.
Absolutely. So it's actually been a many-year kind of process. When I first started coming to supercomputing, there were one or two quantum talks, maybe a booth over in the corner, and we've been talking about quantum for a while now, and every year it's kind of increased here, and now it seems like definitely one of the most important topics. I think the community is looking at AI and quantum computing as the two big elements to the future of supercomputing.
And despite the run-up in some of these startup quantum stocks this year, most people still don't understand what quantum is. It's kind of funny, but and understanding what Nvidia is or quantum is to Nvidia is kind of a little bit difficult. We have, first off, quantum is not one technology; it's many technologies. There's several companies working on different types of qubits and quantum computers, and then there's companies like Nvidia that are really working on the enablement of quantum computing. And you've got two key solutions out there. One is CUDA-Q and cuQuantum. Make sure I don't get those confused. That's cuQuantum. So can you tell us a little bit about those two solutions and how they're really enabling quantum development?
Yeah. So, first of all, as far as NVIDIA and quantum computing, we see it as really kind of core to what NVIDIA is great at and what we want to do. This is a new accelerated computing technology based on new physics that's not going to replace the technologies that we have today, but is going to augment them and result in new, more powerful hybrid supercomputers. And we know exactly how to deal with those kinds of problems, how to take a new technology, build the right software and hardware platforms, integrate it with the technology that came before, and make it easy to use for everyone. And so we're very excited to do that with quantum computing. We don't build our own quantum computer, just like we don't build our own robot, we don't build our own self-driving car. We work to enable every single company that does with our technology and platforms. And so we have CUDA-Q. And so, if you know CUDA is to make it so if you know how to program in C or C++ or Python or any language, you can program a GPU.
Yes.
CUDA-Q is exactly that for quantum computing. It extends CUDA into the domain of quantum processors. And you mentioned at the start, there are many different implementations of a quantum processor that look very physically different and are very different to program. And one of the things that's magic about CUDA-Q is it's hardware agnostic. And so if you are trying to simulate a quantum processor, trying to run on one with superconducting qubits or trapped ions or neutral atoms, it still looks like, for the scientist, running your chemistry code or running your material science code, except now augmenting it with quantum kernels. So that's CUDA-Q, extending CUDA to quantum computing. And then what we announced 3 weeks ago at GTC DC and had some major updates on today or this week at Supercomputing is NVQLink. And similarly to how CUDA-Q extends CUDA to quantum, NVQLink extends NVLink to physical integration with quantum processors. And so, NVLink, in short, connects our GPUs together with high bandwidth and low latency, and now connects to our CPUs and partner CPUs through NVLink Fusion. Now with NVQLink, we are bringing quantum processors into that, a low latency, high bandwidth, high throughput, universal interface to any quantum processor. So it's the hardware complement to CUDA-Q.
So the QPU becomes part of the scale-up scheme.
Exactly. So it's just like CUDA-Q, we're doing it in partnership with the ecosystem. And so this week we announced that we're working with 23 supercomputing centers, 17 QPU builders, 6 builders of quantum control systems, which are what sends the pulses and get the data back from quantum processors, to integrate and develop NVQLink.
Yeah, I remember when NVLink used to be proprietary. Now it's amazing how much NVLink has become part of the ecosystem for AI systems, for cloud systems, for everything. I mean, you also made an announcement this week about ARM being a new licensee of NVLink Fusion. So that whole ecosystem around NVLink continues to grow, and quantum obviously being a key part of that for the future. So what about cuQuantum? Where do we go with that?
So cuQuantum is cuQuantum is a CUDA library for simulating quantum processors, and the reason you need that is because quantum processors are developing fast, but they're still not as large as we'd like them to be. They're still not as accurate as we'd like them to be, and there are a lot of important problems to be solved, like development of algorithms and applications to run on future quantum processors, or development of the quantum processors themselves, where you really want the most powerful simulator you can get your hands on. And simulating quantum computing is, of course, highly computationally intensive. If it wasn't, there wouldn't be a need for quantum computing, or it wouldn't be interesting. But the best way to do that is on a GPU supercomputer. And so with cuQuantum, we offer libraries for any type of quantum simulation you'd like to do, be that logical qubits or many noisy qubits, or even kind of more in the realm of EDA for quantum, as primitives, so that they can be integrated into any other partner software. So cuQuantum sits beneath CUDA-Q. If you want to write CUDA-Q code and run on a simulator, you're using cuQuantum. But it also is integrated with every other leading framework for quantum computing. So companies like Google and IBM and Xanadu all have their own simulator frameworks, and they all use cuQuantum to do research on GPUs.
So, to kind of bring this back to the benefit of this is the fact that you're using the AI accelerated, or just the accelerated computing environment that NVIDIA has enabled and created through its GPUs and CUDA to be able to design, build, and simulate quantum circuits and even evaluate that. Is there also a component in there, obviously, because no two qubits are the same, no two quantum circuits are the same. Obviously, error correction has been a big issue, or error mitigation. Is there some components built in to help simulate and or even analyze or help mitigate some of those errors within the quantum circuits?
Absolutely. And so we've had tools for simulating error correction and performing error mitigation for a while. We actually, Google recently had a paper with a claim of verifiable quantum advantage. There they were using cuQuantum for both the validation and some of the error mitigation post-processing. So that's more about getting the most out of today's QPUs. But actually, where we're taking a big step forward now, and where the ecosystem is taking a big step forward, is error correction. So actually decoding errors as they're made in real time rather than post-processing, and doing it in a way where you can imagine driving the error rate of the quantum processor down close to zero, so we can run applications that are fault tolerant. And that's what NVQLink is all about, bringing GPUs and AI to bear on that problem, together with CUDA-Q. And actually this week we announced an initial demonstration using NVQLink with one of our partners, Quantinuum. And so we were able to show that with NVQLink, they can achieve decoding that lowers their error rate by a factor of 5 for logical qubits. The latency that they need is about 30. The latency that we achieve is about 30 times faster than they need, and it's built in a way to scale from the few logical qubits we have now to the hundreds or thousands of logical qubits we want to have in a few years. So they've already integrated our GPU systems with their quantum processor. And so we're very, very excited to see this kind of already delivering results in quantum computing.
So yeah, I guess that's a key point, that this is not one or the other. This is actually a hybrid. This is just extending a hybrid system from the CPU to the GPU to the QPU, and having it all work in real time. And I guess that's a key part of it. Everything we've seen to date prior to this has been okay, you run the quantum circuit usually many, many times,
Yeah.
compare the
Right.
results, and then, try to determine what the accuracy is. Now
Right.
you're saying that we can actually do that in real time and possibly even reduce the number of runs required to actually get that accurate.
Right. And so we talk about a new type of hybrid processor, and it's actually even stronger and more interesting than that,
Mhm.
because when you integrate a GPU with a CPU-only supercomputer, you're not depending on the CPU to make the GPU work.
Mhm.
But in this case, it's actually kind of tightly symbiotic. So the quantum processor is going to create a more powerful supercomputer working together with CPUs and GPUs, but you need the classical computing, and you need it tightly coupled to get the most out of your quantum processor. And so it's really necessary to do now.
Now we're seeing the specialization of GPUs, or I tend to call them hybrid GPUs because they're more of an AI accelerator. But we're starting to see, with Rubin CPX, some of that uh, specialization for different types of AI workloads.
Mm-hmm.
Do you think we need a specialized GPU as we start scaling up quantum processors to thousands or even a million qubits?
We'll see. We certainly need a specialized interconnect. So with NVQLink, we are optimizing for low latency rather than high bandwidth, much more than NVLink. NVLink needs very, very high bandwidth. For quantum computing, you need a lot less, but you need much lower latency. For the GPU itself, I think it will depend a bit on how the error correction is done, which isn't yet a settled problem. A lot of the state-of-the-art error correction decoders have been algorithmic decoders where you'd want high precision, but the trend is actually towards AI decoders. And so, our AI decoders are running on, low and mixed precision, FP4, sort of the direction that Blackwell and Rubin are going anyway. And so I think it maybe mirrors what we're seeing with supercomputing overall, where you have, rather than as many flops as you can cram into a single system, you have a set of workloads that all need different types of compute, and you build your supercomputer with that in mind. And so quantum will be a part of that.
And is there any, especially as you're working with all these different vendors and everything else, and I'm not asking you to, really call out who you think is going to win or what type of qubit you think is going to win, but is it easier to work with certain types of quantum processors or qubits than others?
I mean, I think that there are certainly qubit modalities that are further along in their development than others, where the hardware is more mature and the software stack is more mature. But we think we're still early in the game, right? Everybody wants to get to at least 1 million qubits. Right now, we're talking about 100 or hundreds of qubits, and some of the qubit modalities that are maybe less mature are intentionally taking an approach that has a better scaling story. And so, what we've seen is very smart people pursuing many different avenues, and they're all making progress. And so, it's very promising for quantum computing overall. We think it's a strength overall that there are many different paths to success, and we're not sure there's going to be just one winner. And so, our role is to help them all as much as possible.
Now, the industry is working together on error correction and all the other issues on scalability and everything else. But is there anything else you think the industry needs to come together to solve to actually bring quantum to, practicality?
I think it would be really great to come together and work towards what are the important applications of quantum computing going to be, development of new algorithms and applications, and work backwards from that into requirements and benchmarks. That can be a little more universal and helpful for everybody. And I think that this has been a success of supercomputing. HPL and the top 500 have limitations now, but it's certainly been valuable to be able to quantify success of a supercomputer or power of a supercomputer towards a certain application, and And we haven't yet done that for a quantum processor, in part because the best application, or the first application, is still in flux.
Yeah.
And so, one thing we're trying to do with our partners, and I think a lot of the government programs are starting to do a great job influencing people towards, is as technically and specifically as we can, what are we going to run? What resources is it going to take? What do we need to build? And how do we actually track progress towards that?
Yeah. Well, and Nvidia has done a great job, and most people focus on the hardware, but has done a great job on the software, on the AI side, in developing foundational models for particular vertical applications, as well as kind of a foundation model for foundation models with Cosmos. So, I'm kind of thinking, and I'm not pre-announcing anything here, but I'm kind of thinking that Nvidia is probably going to have some expertise in developing some of those foundation models.
I think we definitely need foundation models for quantum, and we need a few of them. So for error correction, how to understand and reason about syndromes of errors that are streaming in from a quantum processor, and infer from that data what correction needs to be made. It's a very natural AI problem. We're already seeing groups use AI to calibrate and recalibrate quantum processors to understand drift and understand how to optimize the fidelity of the processors as they're bringing them up and right before they're run. And then on the algorithmic side, I think we're seeing tremendous breakthroughs in AI, both in terms of developing hybrid algorithms that incorporate AI and discovering new algorithms. And so I agree with you. I think the future is very bright there.
Yeah. Well, and everything else that we have to do in understanding the entanglement and everything else associated with operating quantum processors. So last year, here's a plug for you for GTC. Last year, NVIDIA actually held kind of a quantum day at GTC, and it was kind of more of an opportunity to introduce, I think, the industry to some of these quantum startups. Are we going to see more of that maybe at GTC this year?
I can't share specifics, but I will say we expect to have a very big quantum presence at GTC. I think if you see what we did at GTC DC and what we're doing here at Supercomputing, it's clear quantum is an important part of the future of accelerated computing, and GTC is about the future of accelerated computing. So please look forward to GTC. We're very excited about it.
Well, Sam, thank you very much.
Thank you, Jim.
If you like this episode, please like and subscribe. And if you have recommendations on future episodes, please let us know. We'd be happy to cover any topics you want. And hopefully, eventually in the future, we can even do deeper dives on how these quantum processors work.
I think it's only getting more interesting.
It is.
Anytime.
It is. Thank you.